not to sort of slavishly, responsibly derive them, which they couldn't do anyway, but to sort of look around and hunt around from some structures that then spit them out, right? So, and there's lots of indications that if this happens, that we're going to find that space-time, local space-time physics, and unitarity, the physics of quantum mechanics, actually have to emerge together in this picture. They can't be treated separately. So let me start getting closer to the content of the talk. So again, I'm going back to this question. You're this experimentalist. Things scatter in, things scatter out. What happened inside to give you the answer? And the usual answer we give going back to Feynman is this is what happened inside, right? The particles came in, they banged into each other, this happened, that happened. There are all these processes. We add up every way that it could happen because it's quantum mechanics. That's why he's famous, right? These pictures reflect space-time, locality in space-time, and quantum mechanics, and make them both manifest simultaneously. And you add them all up, and that's the answer, okay? So, okay, very good. Now, we could just be satisfied with that, except these highfalutin reasons that somehow we want to get rid of space-time and quantum mechanics, right? Or somehow think about them in a different way. So part of the motivation is that if, let's say, the space-time isn't really there, then that's such a huge change in physics that it's very unlikely that it's going to leave everything alone. I mean, it's very unlikely that's something that's going to very slightly modify or add some dumb parameter to our normal picture. Very much like the transition from classical to quantum was huge. You went from deterministic to non-deterministic, and it's not like you can't make classical physics a little bit non-deterministic. It's like being a little bit pregnant. It's not possible. Okay. So how does it actually happen? The way it happens is that despite the fact that classical physics has this clockwork universe deterministic structure as handed to you by Newton, by the time you get to de Maupertuis and Euler and Lagrange, you discover that there is a second way of thinking about what classical physics is in terms of, let's say, the principle of least action. And in the second way, determinism is sort of mysteriously not a star. And it bugged these people. It actually really did bug them. They wrote, sort of pointless philosophical treatises about this. But it bugged them that why is there this second way of thinking about classical physics where the apparently most important feature from Newton is not so important? And today we know the answer. The answer is because the world is not classical. The world is quantum mechanical. Determinism is gone. And so the only way you can smoothly transition from quantum to classical, you can't jump from Newton's laws to quantum mechanics. But the existence of this second formulation of classical physics where determinism is somehow an output and not an input is the formulation that allows you a deformation to jump upstairs to a quantum mechanics. So the thought here, the strategy here, could be completely wrong. But the guiding philosophy of this angle into the problem is that we should take existing ordinary physical processes and where we rely on quantum mechanics and space-time to get the answer, and learn some way of thinking about them where they don't appear. Okay? That's the philosophy. And one important guiding principle, or one important thing that allows us to check, is that, well, I told you we don't know all the rules for how causality, unitarity, locality, and so on are encoded in the amplitudes. In some cases, we know enough about them to be able to check. For example, if you sum the simplest Feynman diagrams, don't have any of these closed loops, they just have trees, then it's already very complicated. I'll show you what they look like in a moment. But let's say someone handed you the answer. Say, here, I did it. You can actually check if they're right or wrong. You can check if they're right or wrong because the answer has to have very specific sort of singularities. Okay? It can only blow up when some of the particles come together and produce an intermediate particle that is real and not virtual. Right? And when that happens, the amplitude has to factorize into two pieces, into lower point amplitudes, have the interpretation that the residue on that pole factorizes into the product of two pieces. That's incredibly non-trivial. If I hand you a random function, it will definitely not do that. So you can check. You can check whether the answer is right or wrong in many cases. And once you start seeing these concrete formulas, and we'll be seeing that in the rest of the talk, they have such a simple structure to them that you can start wondering if there is some other kind of mathematical question that produces objects that do this instead of drawing pictures of that sort. Okay, so that's the strategy that we're going to be pursuing. And if I say it, so that's what I'm saying. So we're looking for now something else inside here, and therefore since our goal is to do this for completely ordinary physical processes, we're not talking about black holes, we're not talking about the birth of the universe, we're not talking about any of those things where ultimately the doom of space-time and so on should matter. Right? We're not talking about that. We're just trying to reformulate ordinary physics. Okay? So the negative is we're not attacking head-on the problems where all these things matter. The positive is that we have data. Okay? That we have theoretical data. We have internal notion of right and wrong. And if you have a new whiz-bang way of doing these things that replaces space-time, blah, blah, you say lots of fancy-sounding words, you have to produce formulas that are right, okay? And you can check if they're right or wrong. So I've spent most of my life trying to interact with experimental data, and it's not as fulfilling as interacting with experimental data would be if there was really exciting new experimental data, but it's the next best thing, because you can know whether you're right or wrong. There's an internal notion of right or wrong. Okay, so let me wrap up this introductory stuff. I'll ask again, is there some deeper structure underlying space-time and quantum mechanics? And I think it's clear that if there is ahead of time, it has to involve new ideas that are both new physical ideas and clearly new mathematical ideas. It cannot be mathematically sterile simply because for the practical reason, the final answers you get for these amplitudes are rich and complicated functions. You're not going to get them from some random, simple little dipsy-do, right? We get them in the standard point of view from all the apparatus, path integrals, Lagrangians, gauge symmetries, all that stuff. If we're going to ditch all of that, there has to be something else of some reasonable mathematical depth and sophistication to do that, even without saying anything else. Okay, so let's, and I'll say this one last time. So if I go back to this, to the motivation that we're going out to infinity, and then the observables are there at infinity. Here, when we're talking about amplitudes, infinity means just whatever data you use to label the energies and momenta and spins of the particles coming in and going out. So that's a canvas. So in this anti-de Sitter space, the boundary was a nice space. It was an ordinary space. It had a notion of time. It had a notion of locality. So if you wanted to do something there as a physicist, you would know what to do. You put a quantum field theory there. You do something with normal physics. This space is apparently much more arid and boring. It's like the space of n null momenta. That's it. That's it. Okay? Or you can write it in various other variables, twistor variables. There's a whole bunch of, but they're very simple variables. They tend to be just linear spaces. What I'll focus on a lot of this talk are just four-dimensional vectors for every external particle scattering. Okay? So we have a 4 by n matrix. What are you supposed to do in the space of 4 by n matrices? Some question in the space of 4 by n matrices has got to produce answers that we can compare to experiments at the LHC. Right? But what could it be? There's no time, there's no obvious notion of locality, so we have to ask what ideas breathe sort of physics life into this space. And the ideas involve these notions of positive geometries. Now we're getting into the heart of the matter. So, and as you'll see, there are ideas that are at base combinatorial. Then they have a geometric avatar, they have an analytic avatar, and then presumably a lot. There's still a lot that we don't understand. So presumably there's extensions beyond these things. All right. So first, let me define. At least give a rough definition of what the positive geometries are. So positive geometries are simple examples of positive geometries are like in the inside of an interval, the inside of a triangle, a simplex, or the inside of polygons or polytopes in affine spaces, or better in projective spaces. Okay, so and they're one important characteristic is that there's some region P with the property that they have boundaries of all codimensions. There's compact region P with the property of the boundaries of all codimensions. Codimension 1 boundaries, codimension 2 boundaries, all the way down to points. So on the one hand, there's a real geometry here. Associated with this geometry, so here I'm starting from the geometric part. Then there's something sort of on this side, there's some sort of combinatorial ideas that tell you what the interesting these geometric regions look like. But anyway, let's just start with these geometric regions. Then there's something analytic associated with them. That given some region, there's a certain canonical form, differential form, same dimensionality of the space that this lives in, which is unique. It's a unique differential form that has the property of having logarithmic singularities on and only on all the boundaries of P. So logarithmic singularities means that there's some choice of local coordinates in the neighborhood of all the singularities where the form locally looks like the wedge product of a bunch of dx over x variables. Okay? So this is a complex form, but it's a slave to the geometry. Okay? So some simple examples. Actually, I'm missing a slide. Now, you can have very simple, maybe I should say one more thing. So, I gave you examples like polygons and polytopes and so on, but one of the interesting things in this story is the generalization of notions like polygons and polytopes into very, very naturally into slightly more interesting spaces. So the object I'm going to tell you a lot about in the next 20 minutes or so is the amplitahedron, and you can think of the amplitahedron as simply a generalization of polytopes into the Grassmanni. So instead of a projective space, it's a notion of a polytope that makes sense in a Grassmanni. Actually, a number of my math friends told me that apparently Galfand was going around in the 90s telling people who worked on polytopes that you're working on boring things all the time. You should figure out how to generalize polytopes into the Grassmanni. And that's exactly the thing that we'll be talking about. But also other things. There are positive parts of toric varieties. So you can go beyond polytopes and polytopes. But typically there tend to be very simple spaces where you know the form. For example, if you have an interval, there's some variable x, and you have an interval that has between a and b, that could be the positive geometry. And the canonical form would just be d log x minus a over x minus b. Or dx over x minus a minus dx over x minus b. Okay, so that's one form of logarithmic singularities on the two boundaries, sort of trivially.
What does positive refer to? What's
positive? Good. Positive here refers to the fact that we're talking about the interior. And that's because every point on the interior is a positive linear combination of these two coordinates. Okay? So we'll be reviewing that in a second. But the notion of positivity has everything to do with the interior. So to talk about the interior of any region is associated naturally with the notion of positivity. Okay? But you can do fancier. You can do a triangle, and then if the lines that define the edges of the triangle are just linear functions L1, L2, and L3, there's a 2 form, which would be d log, for example, L1 over L3, d log L2 over L3, and you can choose any one to be downstairs. They're all the forms of the same design. But then it gets a little more interesting when you have a quadrilateral, for example. Okay? If you have a quadrilateral, it's not so obvious how to build a form just totally trivially. It would have to have 4 poles. If there are these linear factors defining the lines here, it would have to have, so if the ambient space, I don't know, if the coordinate x, y in the ambient space, I might write down something like dx, dy over L1, L2, L3, L4, but that's not enough, because what's very important is that it has logarithmic singularities on and only on the boundaries of the space. What that means, back in this example, it means if I take a residue of this 2 form on any of the poles, for example, that one, then the residue is a 1 form, and that 1 form is the canonical form on the boundary. Okay, so it only has singularities there and there. Now, if I apply that to this example, clearly I can take a residue, let's say where L1 is 0. But if I do that, in principle, I could have 3 poles on this line. That point, and that point, too. Okay? And similarly, I could have another pole over there. And so what you need to have is a very special numerator here, which is in fact just a linear factor that's the line that passes between these 2 bad points. To put zeros on those bad possible residues, in order to be left with something that has logarithmic singularities, not just in codimension 1, but in codimension 2, on and only on the boundaries of the space. Okay?
Once again,
Yes.
why is it called positive geometry? Did you make it up?
Yeah, well, yeah, that's right. It's just a name that we're giving it, and it's simply, huh?
It's a new name.
It's a new name, that's right. And in the case of polygons and polytopes, it's just the inside of a, it's just the inside of a polytope. The interior. And in this case, the word positive, we'll review in a second, but again, if I have coordinates, you know, if I have coordinates z1, z2, z3, z4, and I have points y inside, all the points y inside are of the form c1, z1 plus c4, z4, projectively where all the c's are positive. Okay? So positivity just means that's a notion of positivity.
So it's a little bit like a convex hull.
That's right. In this case, it is a notion of convex hull. That's right. So one thing the amplitudehedron does is generalize the notion of convex hull into the Grassmannian. So, and it has some of the properties of polytopes and not others. So it's an interesting stuff. Anyway, in general, it's not so easy to take literally the definition and figure out what the canonical form is. And so, just to give you an idea, there's a few techniques for computing canonical forms. And for instance, if you have a complicated positive geometry, you can break it up into simple pieces where you know the canonical form. You can triangulate it. Then if you tile a positive geometry by pieces, so the canonical forms add. Okay. Another thing you can do if you have a simple positive geometry and you find an interesting real diffeomorphism that pushes this interior into a more complicated one, then it's a nice fact, not a trivial fact, that the canonical form on here is obtained by pushing forward the simple canonical form you have there, and so on. So there's a variety of techniques for computing these canonical forms. All right, so keep that in mind. Okay, so those are some of the kind of mathematical objects we're going to run into. All right, and now let me go back to really set the concrete stage for the physics. Let's go back and look at the LHC. And our experimental friends collide billions of particles a second. And if you're lucky and you're looking for things like supersymmetry or whatever, you'll maybe make one new particle a minute. Okay, so that gives you an idea of how gigantic the ordinary background is that you have to subtract in order to see the signals for the new stuff that you're looking for. So that means that you have to be able to calculate with really high precision the rates for everything that could be happening from completely ordinary standard physics. And the protons are big messy bags of particles. They're made out of quarks inside that are held together with gluons. And the dominant thing that happens, or one of the dominant things that happens, is like two gluons come in, and they hit each other, and two gluons come out. Or three gluons come out, or four gluons come out. And we don't literally see the gluons when they come out. They like turn into, strongly interacting jets of particles. But we can really think of for all intents and purposes, we can think of these gluons deep inside the protons, effectively massless particles that come in, they hit each other, and they break up into two gluons coming out, 3, 4. For practical purposes, experimentals need the answer to this question up to like maybe 6 or 7 or 8 gluons coming out today. Okay? Okay, now this is not a problem. This is completely good old-fashioned textbook physics. Okay? And for instance, if it's 2 in and 2 in and 4 out, to the leading order of approximation, what you're supposed to do is open up your quantum field theory textbook and draw all these Feynman diagrams. So this is why Feynman is famous, right? Feynman is famous because he told us how to think about all these things. So we're supposed to draw all these pictures. In this case, in the leading order of approximation, you only draw diagrams that look like trees, like this. And it turns out there's 220 diagrams, tens of thousands of terms if you actually do it. Just open up the textbook and just do it. Okay? Now, you might think, tough, that's life. It's complicated. Not every question has a simple answer. And part of the chauvinism of our part of physics is to declare as interesting only those questions that have simple answers. And the rest of it is some kind of engineering. Okay? So some poor person has to sit down and calculate these things. But so what? It looks very complicated. But physics, and I suspect mathematics as well, but I don't know. Physics has a way of rewarding morally correct behavior. So somebody had to do this, and the people who did it found a stunning surprise. So first of all, this is what it looks like if you do textbook calculation, literally. Okay? It's about 100 pages that looks like this. This is not even 2 to 4, 2 to 3. but you just do it, you shove it in the computer, do it anything, you get like 100 pages of horrendous mess. 2 to 2, you put on a problem set, and 3/4 of the students, half of the students don't do it, so you don't take them as credits. So it's doable. Not super easy, but doable. 2 to 3, complete nightmare. 2 to 4, totally forget about it. And yet, people around 30 years ago found by many tricks, using supersymmetry, using tricks, of a sequence of several years, they found that those 100 pages of algebra collapsed to that one-term expression. Okay. Now, there are these pluses and minuses there, and that reflects that the gluons have spin. Okay, so the gluons are massless particles. If they're photons, we'd call it polarization, right? So we have positive circular polarized, negative circular polarized. So depending on the helicities of the gluons, in the case where, like in this, 2 of them are negative and the rest are positive, that's stunningly simple one-term expression. And I'll define similar variables a little bit later, but each one of these little brackets is, roughly speaking, the square root of the momentum of a particle. Okay, so that little anyway.
So this is a new result, or it's...
No, this is 30 years old.
But you have a new
31 years old. Huh?
So you have a new approach?
Yes. So this should make manifest that, or should give you a clue that Feynman's way of doing the physics, which is the way where spacetime and quantum mechanics are king, manifest, it's correct. Manifest those rules, but it's hiding something else. Right? So there's some extraordinary new structure that should make these things obvious. Okay. All right, so the first part of the talk, a little too long, all this mumbo-jumbo about quantum mechanics, space-time, locality, gravity, blah, blah. We should maybe philosophically look for some new way of thinking about scattering processes. Now, this is super practical, right? Super practical and with the same thing. You try to make space-time and quantum mechanics manifest. It's correct. You're also led to think that the answer is 100 pages of algebra, when it's in fact one term. Right.
So what is the thing that precedes the exclamation mark? I don't understand what it means. In other
Sorry,
words,
what?
the hundreds of pages were a bunch of diagrams. We
Yes.
were going to compute a diagram in the end, or what was
No, it's one process. That means that those hundreds of terms have a gigantic, very non-local cancellation between them, and they collapse to this.
But I don't understand the notation.
Yes. I'll explain what the notation means later. I mean, suffice to say, it's not defined to equal the sum of 100 pages of algebra. Okay, so but I'll introduce. I'll be more precise about what the notation means. I'm still being a little. I'm being a little. Impressionist. All right. And in fact, it's more than around 10 years ago. So back then, I should say, people didn't appreciate this was the tip of a big iceberg. Okay? It was not. And part of the reason was the simplicity seemed to be in still some. For instance, if you did the case where 3 were negative and 3 were positive, that was still very complicated. So people thought maybe there's something very special. It was not obvious that there's something general going on here. Today, we absolutely know there's something general going on. We just don't know exactly what it is. But just so you have an idea that this is also not super duper esoteric stuff. It's not just that there's remarkable simplicity. The remarkable simplicity is associated with some hidden symmetries. These amplitudes have a hidden symmetry. Now, at tree level, where we only draw these leading diagrams, even in that approximation, they have this symmetry. The symmetry could have been discovered in 1954, in principle, when this theory was first written down, and people knew where to look. Okay, so the expressions existed. You could, in principle, have discovered at any point in the last 60 years, but it was not discovered until around 10 years ago. And roughly the symmetry is this. So here, imagine that the particles coming in have momenta of P1, P2, P3, and so on. So all the momenta add up to 0. Because they add up to 0, it's useful to sort of draw them end to end on a 4-dimensional piece of paper. So they close into a polygon. So if I call the vertices of the polygons x1, x2, x3, x4, and so on, then the amplitudes turn out with a few little caveats, or a few extra decorations. But basically, the amplitudes are invariant if you invert the x's. There's inversion. You invert. Now these are not positions. These are these x's of units of momenta. So this is in a momentum space. In fact, this is associated with conformal invariance, and in fact, this is a dual conformal invariance. The conformal invariance not in the ordinary space-time, but in a dual space-time whose coordinates are momenta. Now, in fact, this theory of gluons in the classical approximation, which is what we're talking about when we just draw these trees, is conformally invariant, although in the usual sense. So we have these two symmetries. There's a conformal symmetry in ordinary spacetime. There's a dual conformal symmetry. And if you start commuting those symmetries, you get an infinite dimensional Yangian algebra. Now, if you talk about the maximally supersymmetric version of these symmetries, then it becomes appropriately supersymmetrized. The theories that we're talking about are exactly conformal, even taking all these loop corrections into account, quantum mechanics into account. And so there's the Yangian symmetry of SL4/4, which is completely invisible in the Feynman diagrams and the Lagrangian, none of it. And you see it has to be, because the Feynman diagrams are built to make one spacetime obvious, but this is telling you there's a symmetry in another spacetime, in this dual spacetime whose coordinates are momentum. Okay? Now, even this might seem like some kind of fancy schmancy thing, but I won't have time to explain this. It turns out that this Yangian symmetry, in fact, contains and generalizes the ancient Runge-Lenz symmetry that explains why the Kepler problem is integrable. Okay? So the Kepler problem is integrable because there's a hidden SO42 symmetry. Okay? And that is actually absolutely content. That symmetry lives inside this SL4. And so this is one of the lovely things that these things that seem relatively esoteric, these mysterious things that have been lying around for 400 years, they don't go away. And that Runge-Lenz symmetry, in fact, its relativistic extension and generalization is exactly the thing that's showing up here. So the question, where does the Runge-Lenz symmetry come from? Why is it there? Is now transmuted in this language. Why the hell does the maximally supersymmetric theory of gluons have an SL4/4 symmetry? Where does this infinite dimensional symmetry come from? It's completely invisible in confinement. Okay, so
can you say what is the SN4/4?
sorry?
Is it supergroup or something?
Yes. It's the Yangian of the supergroup SL4/4. And yeah. Okay, so all of this structure has been sitting under our noses for 60 years. And so what we're beginning to see is ideas from string theory, twistor theory, Penrose's ugly duckling for a long time, integrable systems, spin chains, as well as these new structures in geometry and combinatorics that I want to tell you a little bit more about, are pointing towards some new formulation of completely standard physics where we can see spacetime and quantum mechanics as emergent ideas and not fundamental. All right, so I'm out of time, officially. And don't worry, I'm not going to go through all the remainder of the slides in equal time that I've spent so far. But what I'd like to do, if I can have maybe 10 more minutes, is that okay? What I'd like to do is just somewhat impressionistically give you an idea of what some of these structures look like. And just as I mentioned, there need to be new physical ideas and new mathematical ideas, and I want to give you some flavor of what they both look like. Okay. So let's first talk about the physical ideas. And if we go back and think about scattering processes, the very simplest scattering amplitude you can talk about of all is one where just 3 elementary particles come together at a point in space-time. Not 2. 2 doesn't make any, 2, there's nothing going on, because by momentum conservation, the particle is just moving in a straight line. Okay, so there's no scattering involving 2 particles in that sense. The first interesting thing is where 3 particles come together at a point in space-time. And this turns out to be so constrained that the structure of these interactions are completely fixed by Poincare symmetry. Okay? Up to an overall strength of the coupling that I'm not even writing down here. So since someone asked before, I might as well define some of these variables now. We'll be defining closely related ones later. But the idea is very simple. If you have any form momentum, p mu, which has a 0 component and a spatial component, there's an associated 2x2 matrix, which is just what you get by dotting these with the Pauli matrices. So it's P0 plus P3, P0 minus P3, P1 minus I, P2, P1 plus IP2. And you'll notice that the determinant of this matrix